So if you have two particles having their masses, they somehow have gravitational force. And that gravitational force is also inversely proportional to the square of the distance, but now you have m1 times m2. So in that sense, Coulombs law is a cousin or a brother of Newton's law of universal gravitation. But think more carefully. You have to be extremely careful and sensitive. In terms of amplitudes, Coulomb's law is identical to Newton's law. But they are dramatically different in one special aspect. And what is that? Well, in our daily lives, masses are always positive, right? So think about it. The dramatic difference between the two laws comes in the fact that charges are allowed easily to have different signs, positive charge or negative charge. But for masses, I mean, to the world that we're living in, masses are positive. So basically, for Newton's law of universal gravitation, if you have two masses, they always attract each other, right? But for Coulomb's law, if these two charges are having the same sign, the forces are used to repel each other. And if the two charges are having opposite signs, the forces are used to attract them together. So at this time, you must understand what I mentioned. Static electric field. Everything you study here is fake, right? I mean, how can you have two charges sitting there without moving? It's impossible. Coulomb's law tells you there are forces between the two charges, right? Once they have the force, they would be used to expel each other or attract to each other. So charges would start moving. So in the real world, things become complicated. But here in the classroom, and for your understanding of this, we make the assumption everything is being stationary. Nothing is moving. So that is a super strong assumption, right? Now, what happens when the charge distribution is becoming more complicated and even continuous? In the previous case, we only considered two discrete charges. You can easily write the formulation. But what happens if your charge distribution is you have lots and lots of charges, eventually it becomes continuous. Don't worry, it's okay, because basically the first postulate, divergence of E is equal to rho divided by epsilon, is a linear equation. So all you have to do is add. So assume in space you have charge distribution 1, which is giving you E field intensity number 1, but nearby you have a second charge distribution is generating its own field pattern. Now you mix the two together. You put the two into the same box. What is going to happen? Well, math tells you it is linear, so you can add them together in any proportions. C1, C2 is just a coefficient. Okay? So if you mix these two together in any ratio, it's okay. All you have to do is, well, E1 and E2 is multiplied by the corresponding same ratios. Right? So there's nothing to fear. Coulombs law tells us, once we know the force between the two charges, we have more charges, we just add them all up. Okay? Because we have a linear relationship. So later on, we are going to investigate into two particular cases. The first one is if we have multiple discrete charges. So we might have 5 charges, but each one is a discrete entity, a discrete particle having certain charges. So that's case number 1. Case number 2. What happens if the charge is really continuous? Are we capable of finding the resulting field distribution? So let's wait and see. Okay, first case. We have discrete charges. So we have lots and lots of charged particles. Each one is having its own coordinate position. Okay. So I'm going to explain the nomenclature, mathematical terms I'm using here. I now have an observation point, so I want to know what is the total E field strength and direction at this P point. So this is my observer. I'm standing here. I want to measure the E field intensity here at this location. So that means I need to know the position, right, for this observation point. And that position is itself a vector, r, right? I'm using r to express as a generic position. It can be x, y, z, it can be r phi theta, r phi z, or r theta phi. Doesn't matter. So this r stands for my position vector of my observation point. On the other hand, I have lots and lots of charges. So Qk means the kth charge. For the kth charge, it has this quantity. Qk means the charge, the amount of charge for my kth particle. The charge has its own position in space. Now, to differentiate these two, the charge, I'm trying to differentiate the charge position from the observation point. I'm using the prime system. So this Rk prime, so once you see it, you know, oh, this is mentioning about the position of the kth charge because you're having this prime here. Okay? So I'm using the prime coordinate to denote it is representing a source, a charge. The unprimed system is used to express the observation point. Okay, so this is my charge. For example, this is my first charge, and this is my observation point. I know the positions of both. Then I should be capable of knowing the distance between these two, right? The distance between these 2 points should be r, the observation position vector, minus the position vector of my kth charge. R minus rk prime, and then I add the absolute value. That's the distance. For your reference, I'm showing you here this rk vector is r minus rk prime, both vectors. So the unit vector is the vector itself divided by its amplitude. This amplitude is r vector minus rk prime vector absolute value. Okay? So this is drawing for only one charge. but that charge might be the 99th charge in space. With that knowledge, I can quickly write down, well, if I have n charges, each one of them is dispersed in space. So each one of them has its own position vector, but that's okay. All I have to do is add them up. And remember, this ARK unit vector is different for each charge. Why? Because each charge is having its own position vector. So basically, its RK is different for each charge. So the direction and magnitude are different for each charge. So all I have to do is add them up based on my understanding to Coulombs law. Right? Each one of them is setting up its own E field intensity, which is inversely proportional to the distance from the charge to the observer. And the direction is defined by the unit vector and the sign of the charge. Now, the second expression, I want to replace the unit vector by this expression, highlighted in yellow box. Okay. They are the same thing. It's a different way, just explicitly writing out the unit vector. So all I have to do is add them all up. Straightforward and easy, but now let's look at a real, well, example. So example is, well, you have all these derivations in front of you, but my recommendation is they are extremely easy, but try to work on your own. Just cover the answers and try to work on your own. Now, I'm only having two charges, Q1 and Q2. The first charge is having 2 coulombs, and it is seated at a position in the Cartesian coordinate 1, 0, 0. The second charged particle carries a negative 3 coulombs, and it is situated at 0, 1, 1 position. And the question wants you to answer, what is the net, the total field intensity at an observation point of 1, 1, 0? This is like going back to high school, right? The main point is whether you're able or not to calculate vector analysis. Okay? So try to work on your own. I will explain it slowly, and when I finish, you can compare your result to my result. Okay, we know the observation point. We know its vector, 1, 1, 0. We know the position vectors for the two charges. So the first thing is, so R1. The R1 vector is my observation position vector minus my first charge position vector. So this is 1, 1, 0 minus 1, 0, 0, so it's 0, 1, 0. So its amplitude is just 1. Okay? R1 is 1, so you know this R1 is 1. I could repeat the same procedure for the second charge. R2 vector is my observation position vector minus the second charge position vector. So now it's 1, 0, negative 1. So in this case, the distance from the observation point to the second charge is square root of 2. Okay? Now, once you know this, so this is the vector and this is the amplitude, you basically know everything. So all you have to do is invoke this equation and you sum them all up for the two charges. K equals to 1 to 2. You only have two charges. You're lucky. But I can guarantee you during examination, I won't be so nice. At least 3 charges. Then you're going to hate me. Now you like me. Alright, so basically just add them all up. Don't ever forget the charges comes with a sign. The second charge is carrying a -3 coulombs. Okay, so this is why you have -3. Basically, just add them all up. So a very simple problem, but it's really testing on your ability to perform vector adding, subtraction. And that's it, right? Such a simple problem gives you this complicated answer. So, how many of you are getting the same result as I am? I hope I'm right. Alright, so take a look. I'm not teaching you a lot of stuff. I'm merely showing you. Once we follow Coulombs law and we know how to properly formulate the E field intensity of a single charge in a quantitative sense. Quantitative means I know its magnitude, I know its direction. And that's extremely helpful because once we know the E field for a single charge, we can extend it into charge distributions. So this example shows you I have multiple discrete charges, and next one I'm going to show you what happens if I have the two charges but in a very unique way. Okay? In this case, it's called an electric dipole. It's a very fundamental building block to our understandings to the world of electromagnetic waves. So later on, I will come back to electric dipole multiple times. So electric dipole is arranged uniquely. You have two charges separated by a distance of d. So this position vector is defined from the negative charge to the positive charge. So these two charges have the same amount of charge, but they have opposite signs. Okay. So this is positive Q, this is negative Q. And by convention, the position vector is defined from the negative charge pointing to the positive charge. So this D itself is a vector. Okay? Alright, so let's try to extend what we know already. Directly, I can just write down the total field intensity due to these two charges. One is positive, one is negative. Right? I have an observer, so the observation position is R vector. These two charges have their own distance vectors relatively to my observation point. So for the positive charge, this is R vector minus D divided by 2. For the negative charge, it's R plus D divided by 2. So we have a total of 3 position vectors. Right? And that's the reason why you have this result. Okay, so this is straightforward. I mean, once you understand Coulombs law, you can write down the field expression directly. But what is more interesting is what happens if the observation point, this R, this distance, the magnitude of R position vector, is far, far larger than D. Meaning we're very far away from these dipoles. What happens? So this is a mathematical trick. So this blue part, 1 over R vector minus D vector divided by 2 cubed. I want to find some approximation, right? So its magnitude negatively cubed means this 1 over this. Okay, so that is equal to the square and take the square root. This is purely math. You multiply everything out you have this 3 contributions. And now we want to make approximations, and usually by knowing that we are very far away from the dipoles, so this R magnitude is much, much larger than the D magnitude. So which one of the 3 terms can be cancelled out or ignored? The last term, right? R squared as compared to D squared is very big. So you have a very small value divided by a very large value. This one can be ignored. Then you know this first item, 1 over this blue part, can be approximated by this expression. By the same analogy, the red part can be approximated by this value. So you have all this in front of you, so I can go slightly quicker. What I want to tell you is, having this expression helps a lot to our understanding to the voltage we're going to introduce later. Okay? So up to now, I'm showing you this is one example again to use Coulombs Law for discrete charges. But when you are far away from the charges, you can further make assumptions and simplify your result. But let me just stop here for this case. I will come back to it. Okay, when the time approaches, I'm going to notify you this. But for the very last 2 minutes, I promised you Coulombs Law can be applied to having multiple discrete charges and even a continuous charge distribution. So if in this structure I have lots and lots of charges, can I still try to find out the resulting E field intensity pattern? Yes. So in this case, all you have to do is each differential portion would contribute to a part of the total E field intensity. So all you have to do is perform integration. So once you have a continuous distribution, instead of having summation, summation is for discrete charge distribution. When you have continuous distribution, you use integration. So if a charges are distributed in a 3-dimensional volume metric way, you have a volume integration. If the charges are dispersed in a surface aspect, you perform surface integration. And if you have a linear, a line-like distribution, you just integrate using line integration.